right. So anybody having any specific problems before we jump into chapter 13 on equilibrium? I see Isaac, but I see Isaac's name, but I don't see Isaac. Are you really there, Isaac?
Yeah, I'm here. I've got my daughter.
Okay. That's fine. All right. We'll look at chapter 13 on equilibrium. So let me share the PowerPoints. Start the show. Let's try that again. There we go. Kessa's here. Hi, Kessa. You're behind. You're behind the wheel again.
Yeah, I just got off work.
Oh, okay.
Yeah, I was supposed to get off at 8:30 so I could go ahead and be home, but I'm going to be behind the wheel for a little while because I got to go and take the truck over and have the window fixed. So I got to go pick the truck up, but I can still pay attention to you on this.
Yep.
I know that you're busy teaching, but I need to tell you something. Last Thursday, whenever I was on Zoom, I got kicked off of Zoom and I got kicked out of Blackboard and I got kicked out of email and I couldn't do anything. Like I couldn't access Cengage, I couldn't access anything because of something was wrong with my Blackboard. So I went back in and rewatched the video from last week, but it kicked me out and I couldn't email you, and I figured I'd just tell you this morning.
Okay, have you got it sorted out with IT already?
Yeah, I got it fixed. I got it fixed yesterday afternoon.
Okay, good. All right, so let's see. We're going to look at chemical equilibrium today. And we needed to take a look at kinetics first, because equilibrium is intimately tied to kinetics, and an understanding of kinetics is essential to appreciating what equilibrium is all about. So let me move some of this stuff out of my way so I can see what I'm doing. Here we go. All right, so what do we mean by equilibrium? Well, there's Heather. Okay. We got you. Everybody who's going to be here is here. Steffi spent the night in the hospital, so she won't be here today. Equilibrium. What do we mean by equilibrium? For chemical purposes, an equilibrated system, one that is at equilibrium, is one in which we don't see a change in concentrations of either the reactants or the products. And that's a general statement because some systems reach equilibrium where they're mostly reactants still, some of them where they're mostly products still, and some of them are more evenly divided. So that's a different topic, and we'll touch on it in just a few minutes. What we need to, the tie-in between equilibrium and kinetics has to do with the microscopic level. At the molecular level, things are happening at a furious pace. What you see is that the forward reaction produces products, but the reverse reaction can reproduce reactants just as easily. Let's see, here we go. So what we'll see is using this Haber reaction as our example, the forward reaction from reactants as nitrogen gas and hydrogen gas to ammonia is what we'd normally consider the reactants and products, but the reverse reaction can also occur. And if you start out with just reactants, in this case, nitrogen gas and hydrogen gas, you see that you've got a lot of hydrogen, you've got a lot of nitrogen, and you got no ammonia whatsoever at the very beginning. Now that's where we would normally study our kinetics when we don't have any significant concentration of products. And that's for good reason, because once you start building up products, then you reach a point where the reverse reaction is balanced against the forward reaction. And then the kinetics appear to just sit there and do nothing. But we know that there's a lot of activity underneath. And that just says the same thing. This is just another way of looking at it. If we look at it from a kinetics angle, the forward rate is all there is in the beginning, and the reverse rate is nothing. Then the reverse rate starts to increase as we generate more product, and the forward rate decreases until we reach a point where they balance one another. Okay, so here this is kind of a teaser where we have this reaction as our example. Water and carbon monoxide react to produce hydrogen and carbon dioxide. Well, what do you think would happen, since we know that at equilibrium, the forward rate is equal to the reverse rate? Then we're producing products at the same rate as we're producing reproducing reactants. Then what would happen if we add more water to the flask? We would expect that to, if we're at an equilibrium situation, if we add some more reactant, that would tend to boost the forward reaction somewhat until we reestablish an equilibrium state. Similarly, if we add more hydrogen to the product side, that would favor the reverse reaction until we reestablish equilibrium. Now this brings us to the quantitative expression of equilibrium. Once you have the balanced equation, and these two Norwegian chemists are credited with developing this law, the law of mass action, Peter Weg and Goldberg. And what they said was that if you have the balanced equation, and that's important, then, well, I'm getting ahead of myself. They divided studies of chemical reactions into two categories. Either the rates of reactions, which we now call kinetics, they call chemical dynamics. And for reactions that can reverse, they call those statics. And static is just derived from a Greek word that means not moving, or dynamics means moving. So their interest was particularly with solutions, chemistry of solutions. So they naturally expressed this law of mass action in terms of concentration. And now if we go to our hypothetical reaction where A and B react to produce C and D, then you get a situation where this expression is equal to a constant value. And unlike the overall reaction for kinetics, where you cannot you cannot use the coefficients to derive a kinetics equation for equilibrium, the balanced equation is required to generate the expression for the equilibrium constant. And that's what this K means. That's the equilibrium constant for this balanced reaction is equal to the product expression raised to each power divided by the reactant expression raised to its respective coefficient power. Notice that the product is in the numerator and the reactants are in the denominator. That's always the case. So that gives you some indication as to what you can expect from when you start plugging in real numbers. If your reaction largely goes to completion, the K value is going to be very large. And if the reaction is such that very little product is produced at equilibrium, then the K value is going to be very small. Another convention is the square bracket. The square bracket is reserved for expressions where we know we have an equilibrium situation. It's the concentration of C at equilibrium. If we have parentheses instead, we're implying that the system is not at equilibrium, right? And we'll introduce calculations using non-equilibrium situations a little bit later. Okay, another peculiarity about the equilibrium constant is it's never reported with units of measure. I know from the very beginning, first semester chemistry, we hammered the concept of putting in the proper units. And that's important, except that now we're in a situation where the units would be confusing. They would confuse the issue if we had to put units in for every expression. And you can see that if you put units in for each of these concentrations, and then you raise them to different powers, the units for K could be anything. Sky's the limit. So we just have to take extra care when we're generating the K value that we do it properly. Because if we use the K value later to solve this equation for one of its components, then we're not going to be able to fall back on dimensional analysis to verify that we have the right value. Okay, so they're never reported in units. If you look up the K values in reference manuals of any kind, you will not find units for the Ks. Okay, so what would be the K for this reaction if we put the products on the reactant side, right? If we did it like this, what would be the K then? Well, if we just plain write the K for this, then we would put A on top and B on top, and C would be on the bottom because it's now the reactant, and D on the bottom. Right? So what that tells us is we know that the reactions can go both directions. That's how we have equilibrium. So if we want to express the reaction, say we're going to use Hess's law, and we're going to have to add up various reactions to get our target reaction, the final reaction, we might need to flip the reaction in order to get things on the proper side. Well, in that case, you need to know something about what happens to the K, right? In this case, it's very simple. You can see that this is the reciprocal of that one, or that's the reciprocal of this one. So if you know this K for that one, then you know for the reverse reaction, the K for this one is equal to, let's see, for this, that one, it's 1 over K, or K to the minus 1. That number, that K to the minus 1. You just take the reciprocal of it, then you have the K for the reverse reaction. Let's imagine another scenario where when you're adding reaction equations together, you need to multiply your equation by a constant value in order to have enough of something to add together and produce your target equation. If that's the case, we have another scenario here. I want to erase this because I'm running out of room. Let's say we have to multiply this whole equation by some value n. What will that do to the K value? Right? So if K is, in this case, C to the C, what happens here? Well, n times A, n times every one of these coefficients. Right? So that means you got an n here. You got an n there. Oops, made myself a little room here. You got an n there and an n there. Okay? So this is the original K. This is the new K with the n multiplier. So, well, that's not really the K. That's the K, the original K. All right, so that's not true. But what can we do here? Well, we know that math rules say that if every one of these is raised to the same power, then the entire expression can also be raised to the n power. Right? We just factor out this n from each one of those. And what does that mean for the relationship of this expression to the original? Is that now the new K is equal to the old K raised to the n power. So if you have to multiply your equation through by a constant, then the new K value is raised to that power. Okay? I'm going to make myself some more room here. What about that? Okay. Stop me if you have questions. Another factor that might change is temperature. As long as the temperature is constant, then the K value is constant. If the temperature changes, then the K will change. And that's just a simple fact. K is constant for constant temperature. Okay? Now here's another concept that I'm going to throw at you. The difference between equilibrium constant versus equilibrium position. Okay? At constant temperature, K never changes. It doesn't matter what concentration you start with. You start with low concentrations of A and B, and once it reaches equilibrium, do your calculation, you get the K. At the same temperature, you could start at high concentrations of A and B. And once it reaches equilibrium, determine the equilibrium concentrations of your reactants and products, calculate K, get the same value, as long as the temperature does not change. But the equilibrium position can be different depending on the amount of reactants and products that you start with. You could start from the product side, you know, put products in and let it come to equilibrium. But the equilibrium position is dependent upon concentrations. Remember one of the earlier slides where we added a component, right? We're already at equilibrium. If you add a component to that reaction, it starts to shift the reaction to the other side. But it doesn't use up all of the component that you added. It leaves a little bit behind. So logically, the concentration of that added component is not the same when it reaches the new equilibrium. That's the equilibrium position. There's only one equilibrium constant for a given temperature, but there could be many equilibrium positions depending on the concentrations that you start with or that you tinker with over time. All right. So up to this point, we just used K for our equilibrium constant. Sometimes a subscript is useful in describing K. It gives you a little bit more information. If we use KEQ, because K is used a lot in chemistry, right? We just got through with a whole chapter of Ks. We used small Ks in that case for the rate constant. But large K is used under a host of circumstances. So sometimes it's good to put a subscript in here to explain what that means. So KEQ means an equilibrium constant, but it also usually implies that our concentrations are in terms of molarity. That's just understood. Another interesting K has to do with the dissociation of water. Right? If you have water, pure water, it will dissociate into those two ions, right, in solution. And you can write an equilibrium expression for that. And we call that KW. You can dissociate an acid. And we call that a Ka. You can dissociate a base. And we call that Kb. Okay? you can have a solubility product, which we haven't talked about yet, but SP stands for solubility product. F subscript stands for formation constant, and that's probably Greek to you also, because we haven't talked about that yet. Another really important expression has to do with the equilibrium system where all the components are gases, or the only components that enter the expression are gases, and that's Kp. Right? So in that case, using our former example of A plus B equals yields C plus D, then we would need the partial pressure of C times the partial pressure of D divided by the partial pressure of A times the partial pressure of B, and each one of these would be to the power. So this would be a case where we would not need the square brackets, right? They would be redundant. In this case, we're talking about partial pressures because all the reactants and all the products are gaseous. And we can describe the equilibrium situation with partial pressures only. But suppose we wanted, for some reason, we needed to combine this reaction with some other reaction, and we wanted all the units to be the same, right? Instead of partial pressures for gases and molarity for the other reaction, we want them all to be the same. We need to know how to, their interchangeability. Right, for this particular reaction that we've looked at already, we could express this in terms of K sub P, right? Partial pressures of product to squared, reactants to the first power, hydrogen to the third power. Or we could express it in terms of molarity, right? Like that. But these Ks are not the same because we started with different units, right? But fortunately, there is a way to convert one to the other, right? Let me skip ahead and show you that one. We'll come back. There we go. So if you know the K value for the molarity, the KEQ, you can convert to the K partial pressure. All you need to know is what's the temperature and how did the number of moles change, right? So we'll come back to that. Let's go back and finish these other slides first. So in this case, if we have these values that are determined at a given temperature, atmospheric pressure for ammonia, nitrogen, hydrogen, this is at equilibrium, then all we have to do is plug those values in to the expression and calculate Kp, which is 3.9 times 10 to the fourth. Okay, the Kp and the KEQ are have the same pattern in terms of whether they're large and positive or small, and maybe even have a negative power. In this case, Kp is 3.9 times 10 to the fourth, so we know that the partial pressure of ammonia at equilibrium is going to be much higher, and the reaction to the right is favored. Okay, so knowing this K for partial pressures, we can plug it into this right here, put it in that place, and put in the values for R, and for temperature, whatever the temperature happens to be, we'll have to be given that. But how do we know delta N, the change in number of moles. Right? You look at the coefficients, and you take the coefficients of the products, and you subtract the coefficients of the reactants, just the sum. Right? So in this case, right down here in this corner, the product is a coefficient of 2. There's 2. The reactant is 4. So that's 3 plus 1 is 4. Right? And then if we plug those values in, we put the K sub P right here, and then we leave K as our unknown. Our R is the one with liter atmospheres. And the temperature that we're given now is 35 degrees centigrade, which is 308 K. Right? Then we can calculate or solve the equation for K, and we find that our K value is 2.5 times 10 to the 7th with those different units, as opposed to 3.9 times 10 to the 4th with partial pressures. Okay? Now we can also subdivide equilibria into either homogeneous or heterogeneous reactions. The homogeneous should be obvious. The phase of every reactant, every product is exactly the same. In other words, for the reaction we just studied, they're all gases. That's homogeneous. For this other example, hydrogen cyanide or hydrocyanic acid, since it's in aqueous solution, is in equilibrium with its dissociation product of protons and cyanide ions in solution. Everything's in solution. That's a homogeneous equilibrium. Right? So if that's homogeneous, what's heterogeneous? Heterogeneous is one in which at least one of the reactants or products is a different phase than the others. In this case, we start off with a solid, potassium chlorate, and it reacts to produce potassium chloride and oxygen. Right? Oxygen's a gas, the others are solids. In this case, water is split, actually, to produce hydrogen gas and oxygen gas. Those are both heterogeneous equilibria. Now, why are we bothering with this distinction? Because of the way we treat these reactions as opposed to the homogeneous reactions. The homogeneous reactions, every term in the reaction is included in the equilibrium expression. Right? A, B, C, D, they're all there. If, however, one of your reactants or products is a solid, we throw it out. It does not enter into the K calculation. Or if it's a pure liquid, we throw it out. Right? So in this case, our expression would include only oxygen for that K. Right? It would only be K equals, let's do it partial pressure since oxygen's a gas, right, to the third power. That's it. That's the K for this expression because the solids don't count. Now, why is that? The reason that we don't count solids and pure liquids is their concentrations don't change, right? If you've got solid, it's just there. It is. It's not diluted in any way. It's just a solid. So since its concentration does not change, we don't include it in the expression. Liquid water in this reaction, its concentration does not change either. It does enter the reaction, true, but it has no bearing on the equilibrium. So for the second one, our expression would simply be hydrogen, well, let's do it partial pressure. Since they're both gases, pressure of hydrogen squared times the pressure of oxygen to the first power. And that would be an equilibrium expression for the second reaction. Right? You could write it in terms of molarity if you want, that's fine. I have no problem with that. Depends on what you need. Or if you go to a reference manual and you find the K for this expression is KEQ, you know that then you have to take that one and convert it to K partial pressure if you need to solve the equation for pressures. Okay, so solids, pure liquids, they do not enter the expression. They could be, if it helps your thought processes any, you could say that the contribution of the solid or the pure liquid is buried in the K. It's not part of the broken out expression. You just bury it in the K. Whatever way helps you understand, or just memorize the rule. Okay, so I alluded to this one a little earlier. If the value of K is much larger than 1, because the products are part of the numerator, if the value of K is very large, that means the reaction favors products. And the reaction essentially goes to completion. If the reaction, the K is very small, and I'm talking extremely small, 10 to the minus 4, 10 to the minus 10, very small, then the way K is written implies that you still have mostly reactants. And the reaction does not significantly move to products. Those are sort of semi-quantitative derivations of the expression. So if the equilibrium lies to the right, you expect the value of K to be large, right? Greater than 1. If the equilibrium lies to the left, the value of K should be small, or less than 1. And I'm talking a lot less than 1 or a lot greater than 1. When you get close to 1, really all bets are off. And the reason for that is that you have multiple terms that go into the expression. So you cannot say exactly 1. Okay. Now, suppose that your reaction is not at equilibrium. And this may happen if you mix different concentrations of reactants together, and you fully expect, or you could mix reactants and products together in the same mixture. Let's do that. You want to determine which way is the reaction going to go. Well, what you can do is do the equilibrium calculation, but on a non-equilibrium system. And I'll show you how that helps you determine which way the reaction goes. So let's take our generic again, or maybe do we have a, yeah, we'll have to use a generic. So here's our generic reaction. Right? And we normally write the expression products over reactants, but for the Q, and Q just stands for quotient, right? That's what it is. A numerator divided by a denominator is a mathematical quotient. So if we do that, then we put it in parentheses. That implies that we're not at equilibrium. Raised to the power, and then A raised to its power, and B raised to its power. And then we compare that value to the K. Right? We compare the K. If K is equal to Q, then what are we saying? We're saying that the system is at equilibrium. Okay, that's the easy one. What if Q happens to be greater than K? What does that mean? If Q is greater than K, that means we have more product than we would at equilibrium and less reactant, right? Because Q is bigger. This is bigger than it should be, and that's less than it should be. That means Q is skewed toward products. So what does that mean for the reaction process, the progress? If that's the case, then the reaction is going to want to go back to the left. So this favors left movement. Toward reactants. Now here, I want to make a point of this. When we say left and right, if you don't have a balanced equation in front of you or in front of whoever's grading your paper, then when you say left or right, it means nothing. Left and right only means something when you have an equation to reference. Okay? So since we have that equation to reference, I can say it favors movement to the left. And just for clarity, I inserted reactants. It moves toward reactants. Okay? So obviously, if Q is less than K, we have less product than we would expect at equilibrium and more reactant, which means we favor right movement or product movement. Okay? So that's how you use the Q value to determine which way your reaction is going to move. Now, why should we care? Well, besides the fact that it's of practical interest when you're actually doing the experiment, whether it's going to move to the right or the left, particularly if it's extremely exothermic in one direction, right? Then you would want to know, is this reaction going to give off a whole bunch of heat, right? That might be a hazard. Or produce a lot of product, which is mostly gas, right? Then you could have an eruption of some kind. But for our purposes, it's also important to know which way the reaction is going to move because of the calculations that we're going to do later. Because if you know the reaction is moving this way or that way, that determines how you treat the non-equilibrium system to determine equilibrium concentrations, actually calculate them, right? So you need to know which way the reaction is going to go. Okay, I got a cat that wants to exit. Just a second. Here we go. Come on. Okay. There's one case where you don't have to calculate Q, but you know which way the reaction's going. Got any ideas? You set this reaction up, right? Suppose you have something here, you have something there, right? And you've got nothing here and nothing there. Which way is the reaction going to go? To the right, of course. Or if you do it the other way around, if you put some C and D in, and you don't put any A and B in, it's going back to the left. I mean, you don't even have to do a calculation. You know which direction it's going. You could also put in, let's see. Well, if you don't put any B in, you're not going to get a reaction, so that doesn't matter. Okay, so I'm going to leave that up there for a second in case I need it. Here's an example of a reaction of the ferric, or the iron 3+ ion in solution, with the SCN- ion, which is thiocyanate ion. And they combine to form the this complex, right? And your lab this week, which is already posted, I got it done early. Lab number 3 is on Le Chatelier's principle, which we'll discuss in a few minutes. Uses this reaction as one of the one part of the procedures. Okay. So even though the next couple slides do this for us, I'm going to do it up here because sometimes the slides don't show you how you get to that point. So let's say here's our reaction. All right, aqueous solution, and then the thiocyanate ion, aqueous solution, in equilibrium with the iron thiocyanate ion. Okay, and that's aqueous. So first we observe that this is a homogeneous equilibrium system, right? So every term is going to be included in the calculation of equilibrium constant. Let me redo that, and here's why. What I like to do is set up the equation spatially. So that I can do calculations below them and they line up with the balanced equation. Now the next thing you want to do is be sure it's balanced, and it is, right? One of these here, one of those there, one of those there, one of those there. And the charge is balanced also. This is a 3+ here, 1- there, add them together, you get a 2+. So the charges are balanced. Now, what are we given? Well, let's see. For this, we're given, I got somebody knocking at my door, just a second. Come on. Come on. Okay. We're given 6 molar of this ion. Right? And we're combining that with 10 molar of this one. Right? And none of that one. Just put these together, and that's our starting condition. I'm building a table here. It's called an ice table. These are our initial conditions right here. Right? Then we want to see, well, how does it change? And then once we've applied the change, what's our equilibrium situation? We need to know this one in order to do any calculations. All right, so what else are we given? Temperature is constant, and the concentration of this ion at equilibrium is 4 molar. So that's everything that we're given. What we want to calculate is what's the value for the equilibrium constant for this reaction. Now, at first glance, we don't know if we have enough information. So we checked our balanced equation. Now we need to write the expression for the K, right? So it's this equilibrium concentration divided by the product of this equilibrium. Okay. Now, we've already got this one right here. That's given to us. Right? We need to deduce somehow how is this one. So, look what happened. If we started with 0 and we end up at 4, how did we get that change? Well, we added 4. That's the only way you can get to here from there. We had to add 4. Right? So if we got 4, where did it come from? Well, look, the coefficients are 1 to 1 to 1. Right? So the ratio, the change here is that we had to lose 4 from this side. And this 1 to 1, we had to lose 4 from this side, didn't we? That's logical. If we had to add that much, then we had to lose it from here. So what does that give us down here? Where that says we have left this amount, and we have left this amount. Right. Now we have our equilibrium concentrations. We can do the calculations. So we put in 4 here, and I'm going to abbreviate. I just leave out those significant figures for space-saving purposes. 2, 6. Do that calculation. 4 divided by 12 is what? Four divided by 12 is 0.333. So that's our K value for this reaction. The ICE table, or initial change equilibrium, is very useful because it positions all your information logically. Where does it belong? Then you can see at a glance what calculations can be done to accomplish, well, to answer the question. Okay, now that we know what K is, suppose we're given a different set of values to start with. All right, so let's do this, and that, and now we know that this K value is 0.333. Right? But these values are going to change. Our new set of circumstances. Right? So this is going to give us a different equilibrium position, but the same equilibrium constant. So where are we? 10 molar here, and 8 molar here. So now what's the equilibrium concentration of this value? That's the question. What is this one? That one's 0. Okay? So, how does it change? Which way is it moving? It's going to move from this side to that side because there's no product. Right? So, we're going to produce a certain amount of this that we call X. And if we produce X over here, we had to lose the same amount, 1 to 1 to 1. Minus X here, minus X there. Okay? Now, what's our equilibrium situation? Well, we have X there, and it's important, if at all possible, to choose your unknown value so that when you solve for the unknown, that's the answer to the problem. In this case, it is. We want to know what that is, and we chose our X properly. So once we solve for this one, we have our answer. So this one is 8 minus X, and this is 10 minus X. Okay? Now, if we put these values in here, we'll have an equation in one unknown, and we can solve for it. So this one's going to be X in the numerator. This one's going to be 10 minus X in the denominator, and 8 minus X times that. Okay? So we just need to solve for X. Now, anyone who remembers their algebra remembers that if you expand this polynomial, you're going to get an X squared and an X, right? So our expression is eventually going to be a quadratic equation. And solving a quadratic is sometimes necessary. I'll show you a trick or two later that will help us with simplifying the process. But for now, rest assured that this is going to be a quadratic equation that requires a quadratic solution. That's why I think I did it here. Here we go. So there's the table that I just generated up here. And it's hard to tell how I put this together. So that's why I did it on the board. And here we filled in the values. And that's as far as we've gotten so far. But if we resolve this equation in terms of a quadratic format, then we have this is ax squared minus bx plus c equals 0. Remember, whenever you use the quadratic solution, you have to set your equation equal to 0. Right? So that means that x equals minus b plus or minus the square root of b squared minus 4ac divided by 2 times a. That's what that means. And I think that's in useful information. Let me check to be sure. Yes, it's there. The quadratic equation solution is in useful information on that page in the lower right-hand corner. So when you're working problems or when you're taking an exam, be sure and have that page of useful information there with you in case you need that quadratic. Okay, so once we go through the solution here, we get two values, right? That's due to the plus or minus right here.
Hello, this is Jerry with Dr. Patil's office calling for Elizabeth Bly. If you would please return my call at 304-253-1077. Thank you.
So we get two values. We get a 15.99 and a 5. So you have to decide which one is reasonable, right? If you have a negative number, you can automatically throw that one out. There's no such thing as negative concentration. In this case, we have magnitude as an issue. So you look at X, and where did X come from? Well, X came from the iron and thiocyanate, right? So if X is 15.99 and the ratio is 1 to 1, how could you get 15.99 from 10 or from 8? Can't do it. So that eliminates 15.99, and 5 is the only possible. So that makes X equal to 5. And that's 5 molar concentration of the ferric thiocyanate ion. That complex, that's called a complex ion. Okay, we could do this thing over again, right? Just run through the same thing. We'd end up with a different concentration because we started at a different position. So our equilibrium position has changed. But the equilibrium constant is just what it is, a constant. So here's what you do step by step to solve an equilibrium equation. And these steps, you need to remember these because we're going to come back to equilibrium calculations in subsequent chapters. We're not just going to touch on it here and forget about it. It's going to come back. All right. First and foremost, anytime you do any type of calculations with a chemical reaction, be sure your equation is balanced. That worked for stoichiometry in first semester chemistry. It still works. Balance the equation. Then write your equilibrium expression with the reaction the way it is either given to you or that you have derived from the word problem. Okay. Jess is back. All right.
Sorry.
That's okay.
I had to drop the truck off. I'm sure you guys didn't want to watch that.
So when you're doing an equilibrium problem, balance the equation and then write the equilibrium expression for the balanced equation as it is written. Then determine the initial concentrations. So we're starting to build the ice table here. Put in your initial concentrations, and sometimes when you write your balanced equation, you may have to spread it out a little bit to give yourself enough room, right? That way you don't have to rewrite the reactants and products in a table. You can just use the balanced equation and write underneath them. So list the initial concentrations, right? Why do we need to know that? Well, you've got to start somewhere. Plus, if you know the initial concentrations, that tells you which way the reaction is going to move, toward products or toward reactants. And that's important when we start choosing our unknown values. If you're given concentrations for all of the components, reactants and products, then you'll need to calculate Q and determine which direction the shift will occur. If one of your components is 0, like if you're given all of your reactants and only one of your products, and then the other products are 0, you don't have to calculate Q. You know which way it's going. Right? So you can save yourself some time and headache there. You know, unless the question is, you know, what are the concentration? I mean, what is the Q value? Oh, by the way, what if some of your values are 0, right? Say you have your expression here, no, that's wrong. C, D, A, B. What if you're given A and B and C and no D? What would your calculation look like? Well, if you calculated Q with a 0 here, your Q is going to be 0, isn't it? That's less than K, so you know which direction it's moving. So it's kind of not stupid, but a waste of energy. If one of your components is 0, to even bother calculating. If one of your reactants is 0, what does that mathematically say? That says that Q is infinity, right? Anything divided by 0 is infinity. So if one of them is 0, don't bother calculating Q. Unless I throw in a tricky question like that. Right? What if you calculated Q with 0 as a product? What would you get? 0. What if I gave you 0 as a reactant? What would you get as Q? Infinity. Right? So there you go. But if you're given values for every reactant and every product, then you'll have to calculate Q to determine and compare it to K to see which way the reaction is going. All right. Then in your ICE table, once you know which way it's going, you choose your unknown value carefully. And you want to choose it, if at all possible, so that when you solve for that unknown value, you have the answer to the problem. Right? So we'll look at some others, maybe not today so much, but when we do our review document, we'll have some examples there where we have to choose X. And you may see in my worked problems that I didn't choose X very well, because the work problems is an old document, and I wasn't thinking too well in the early days. But we'll use that as a teaching moment and just choose our X better when we work those problems, and show you how it makes the solution easier if you choose your X properly. Then once you've used that unknown value to generate the equilibrium values, even with their variables intact, then you substitute those equilibrium expressions into your K expression and solve for the unknown. Okay, here are some other examples. We'll come back to this if we have time. You can use these as practice, right? Just set up your ICE table just like I did in the previous examples. Plug in those values, reason through what's your best X, your equilibrium expression, and then do the calculations. I'm going to let you do those on your own. And here are the answers. Right, so those are the equilibrium concentrations. In this case, we calculated the value for the product, but we also went back and calculated what's left, right? Because X is part of every expression. So then you can recalculate what are the concentrations, actual concentrations in solution. And notice they have different, even though the K is the same, they have different equilibrium positions for each one of these, right? They're not all the same concentrations. Okay, so let's see. Maybe we can do something with this one. So if we have this as our balanced equation, and it's all homogeneous, well, that's not balanced, is it? So the first thing we have to do is balance the equation, right? So if we've got 2 ends over here, we need 2 here, which means 6 hydrogens, which means we need 3 there. Now notice this is the reverse of the Haber equation. Instead of making ammonia, we flipped it. And now we're making these gases from the ammonia. So we want to balance the equation, and then we want to input, what are we given? Well, 2 moles of ammonia in 1 liter container. Right? So if we have 2 moles of ammonia in a 1 liter container, what's the concentration? 2 molar, right? I'm leaving off the significant figures just to conserve space. All right. So we're starting out with this and none of that, right? Why? Because we weren't given any. We just said 2 moles of ammonia introduced into 1 liter container. That's it, at a given temperature. But we are given, at equilibrium, 1 mole of ammonia remains. So 1 mole of ammonia remains here in what? 1 mole in 1 liter container is 1 molar. Okay? So how did we get there? Well, we lost a mole. We lost a molar. Right? So if we lose one of these, how many of those do you get? Well, for every 2 of these, you get 1 of those. For every 1 of these, you get half of these. It's just the ratio, 2 to 1, 1 to half. Same thing. So if you get 1 of these, then you get 3 times that much over here. Okay? That's why a balanced equation is so important. Besides the fact that you can't calculate K, you need to do these logical progressions. So now at equilibrium, we have 0.5 molar here, and we have 1.5 molar there. So now we can calculate K, right? K is nitrogen. Oops. And notice in this case, it's KEQ. We're using molarity. And that's to the 1st power. Hydrogen to the 3rd power. And ammonia to the 2nd power. Right? So we just plug our numbers in. 0.5, right, to the 1st power, and 1.5 to the 3rd power, and then what do we have left over? 1 molar squared. So what's that equal to? I could get my calculator out, but I think I've already calculated it here. 1.69. Okay. So that's our K value for this reaction. Oh, we're gonna use a different one for the next one. All right. Well, in that case, I better erase this. Right. And in this case, we have dinitrogen tetroxide decomposes into nitrogen dioxide. Dinitrogen tetroxide decomposes, and we're homogeneous again, and the K is given to us. K is equal to 4 times 10 to the minus 4. First off, what does that tell us? That's a very small number, which means even at equilibrium, it's mostly this one, and just a very minor amount of that one. So, starting conditions. 1 mole of this is introduced into a 10-liter flask. So what does that mean? 1 mole in 10 liters is 0.1 molar. It's 1/10 molar. Right? We got none of that. Right? So we know the reaction is going that direction, although not very far. Okay, so we want to know what's the equilibrium concentration of both of them. So we're looking for these values here. Let's say this one is X. So if we choose this one as X, it's going to be minus X because it's going that direction. We're going to lose some of this. And what are we going to make over here? We're going to make twice that much as nitrogen dioxide. So the equilibrium is 0.1 minus X and 2X. And then we can plug those into our equation. So this one's going to be squared, right, because of that. And this one's going to be through the first power. Okay. So it looks to me like we're ending up with another quadratic equation. But here's the first trick. Notice that if this is very small or very large, then the X term can be eliminated from part of our calculation. So we're not going to produce a whole lot of X, which means we're not going to lose a lot of X here, which means X is extremely small compared to 0.1. X is so small, we could ignore it. Right? So that means this one is going to be 4x squared. And this one's just going to be 0.1. And I use approximately. Okay? So now, the nice thing about that is it's easy to do a square root, right? Rather than a quadratic. Because a quadratic, we would have x squared and x in the expression. But if we only have x squared, then we eventually get to the point where we only have to do a square root to find out what x is. So let's resolve this. 0.1 times that is what? Right, bring it over here. That would be 4 times 10 to the minus 5. Right, because we're taking 1/10 of that. And then divide by 4, right, because it's x squared. Take the 4 over here and divide by it. That means we have 1. 1 times 10 to the minus 5 is equal to x squared. So x, we just take the square root of both sides, and then x is equal to the square root of 1 times 10 to the minus 5, whatever that happens to be. Calculate the equilibrium concentrations. Okay, so in this case, x is not the answer. X is only on the way to the answer. So I'm going to have to do that calculation. Let me just take the square root of 1 times 10 to the minus 5. And where is it? Here it is. So x then is 3.16 times 10 to the minus 3. Right? So that means this one is 2 times that, which is equal to 6.32 times 10 to the minus 3 molar, 3 molar. Right? So we have very little of this, not much of that, but we still have lost some of that. Right? So if we take this and subtract that, we get 9.68 times 10 to the minus 2, which is 0.097, this value right here. Okay? So in that case, we couldn't win for losing. Choose your X. You still have to do calculations afterwards. It happens. But we did get to use the trick, right? Because X is so small, and then look, where is X? X is here. Is it really smaller than 0.1? Yeah, a lot smaller. A couple of orders of magnitude smaller. Now, there's a way to prove it, right? It's called the 5% rule. So what you would do is you would take this expression right here and plug in this X value for each one, both of them, and calculate it. And how close is it to this one? If the difference between the calculated one is within 5% of the true value of 4K, then we're good. That's the 5% rule. Okay. You guys are awful quiet. I guess you're just really soaking this up. Now we come to Le Chatelier's principle. And like I said before, this is the focus of lab number 3. And I've got the video posted already. I've got all the information you need in the CHEM104 Blackboard folder. And the report for Le Chatelier, the number 3 lab, is informal. You don't have to write a formal report for this one. You just fill out the document. You can do it by hand, take pictures of the pages and upload those. Or if you have the either the iPhone app that comes with your phone, or for Android phones, you can have the, what's it called? Cam scanner that works for Androids. Then you can take pictures and generate a PDF directly from them and upload that. Okay, so let's get on with Le Chatelier. Le Chatelier's principle is very simple, and we've been using it up to this point anyway. It just says that if a system is at equilibrium, then any disturbance to the equilibrium will be countered by the system in such a way as to reduce the change. Up to this point, we talked about concentration. So if you increase the concentration of a reactant, the system is going to respond by using some of that reactant to reestablish equilibrium. Or if you add some product, then it's going to respond to use up some of that and reestablish equilibrium. But Le Chatelier's principle is not limited to just changes in concentration that we impose, such as adding components or even subtracting components, right? As a product is produced, say we just extract some of it away. That shifts the equilibrium constantly toward product. What happens if the temperature changes? What happens if the pressure changes on a system that's got gases in it? Right? Those are considerations to be made, and Le Chatelier's principle does apply. Right? So let's take a look at some of those. We looked at concentration already. Right? The system just shifts away from the added component or shifts toward the removed component. What happens with temperature? Well, with temperature, K changes, but it's also dependent upon whether or not the reaction is exothermic or endothermic. Right? So let's say we have a reaction where, let's use the usual one. All right. So if our reaction is exothermic, if delta H is negative, right, exothermic, we can insert, for argument's sake, we can insert heat or energy into this equation on one side or the other, right? If it's exothermic, the heat is produced as a product, right? It comes out as a product, right? So we say the heat then is a product. Okay, this is for exothermic. Well, if it's exothermic and you increase the temperature, you're adding energy to the system, which is in effect adding heat to the product side. So that favors the reverse reaction. And this is for exothermic only. You increase the temperature, you're adding heat, it shifts back to reactants. If we decrease the temperature, then we're removing that component from the product side and it shifts back to products. Okay? So you probably know where this is going. If it's endothermic, then the heat component becomes a reactant. Okay, so now if you increase temperature, you're adding a reactant, and the shift is to the right. If we decrease the temperature, then you're removing reactant, and we shift back to the left. Okay. Now this is valid over a narrow temperature range, right? Because we know that the K changes with temperature. So we have to keep this temperature range narrow in order to provide a valid argument in terms of Le Chatelier for a change in temperature. Okay, so that's what happens with temperature. You need to know whether the reaction is exothermic or endothermic, or if the question doesn't tell you, then you may have to make some assumptions, right, about whether the reaction is likely exothermic or endothermic, such as If we take, let's say, octane. Oops, wrong. There. And we react it with oxygen to produce carbon dioxide and water. Right? And you're not told, say we increase the temperature. How would that affect this reaction? Well, you know that all combustions are exothermic, right? So you know that heat's going to be on that side. So there you go. You didn't need to be told that it's exothermic. All combustions are exothermic. Otherwise, your car won't run. That's octane, right? It's in your gas tank. Now, how about gases? So let's look at the Haber reaction. See, we need 2 of these and 3 of these. Right. So now that it's balanced, we know that 4 moles on this side of gas produce 2 moles on this side. Okay? So we're at equilibrium, and we, let's see, what are we going to do first? Decrease the volume. So here's our reaction vessel. And our reactants are in here. Our gases. And we're going to decrease the volume. So we're going to go down to here. How is the system going to respond? Well, what's actually happening? Well, by decreasing the volume, you're increasing the concentration of the gases. Right? You're giving less space for that and less space for that. So how is the system going to respond? It's going to respond as to, you've established a new pressure. So you went from initial pressure to final pressure. And the final pressure is greater than the initial pressure because you decreased the volume. So if we increase the pressure, how can the gas system respond in order to alleviate that pressure increase? Well, the best way is to use Avogadro. Reduce the number of moles of gas in that space, and you reduce the pressure. Right? So how do you reduce the number of moles in there based on the reaction? You shift to the right. You produce more product because you have fewer moles here than you do there. So increasing the pressure produces more product. Okay? Vice versa. If you go from a smaller volume to a greater volume, you are decreasing the pressure. So in order to alleviate that decrease in pressure and increase the pressure, you want to go back the other direction. Right? So if you decrease the volume, increase the pressure, you're going to favor the smaller moles side of the reaction. If you increase the volume and decrease the pressure, you're going to favor the larger mole side of the equation. Okay? Let's see. So what if the moles are equal on both sides? And you make these changes, what's going to happen? Nothing. Nothing will happen. If you change the volume and consequently the pressure, and the number of moles on both sides of the reaction is exactly equal, say 2 and 2 or 4 and 4 or 3 and 3, doesn't matter. If the product and the reactant side are equal numbers of moles of gases, then changing the volume or the pressure will not affect the reaction. Okay. Suppose we increase the pressure by injecting an inert gas. Like if we pump helium into this system, what's going to happen? Nothing. Right? Nothing will happen. Why? Because helium is not a reactant or a product. Just because you change the pressure, you still got the same concentration at equilibrium on both sides. Right? We didn't change the volume. We just injected some inert gas. So we didn't actually change the concentration of reactant or product when we changed the volume. Okay, any questions?
Le Chatelier's principle requires that a chemical system respond to an added stress. If reactant or product molecules are added to a system at equilibrium, the system will shift toward the side opposite of the added component. If a reactant or product is removed, the system will shift toward the side of the removed component. Let's consider an example of a system at equilibrium, the reaction between iron and thiocyanate to form iron thiocyanate. Iron 3 is a light-colored ion in neutral or slightly acidic solutions. Thiocyanate is a colorless ion in solution. The iron thiocyanate complex is a blood-red ion. The reaction of iron and thiocyanate in solution is reversible. That is, it moves in both the forward and reverse directions. Let's consider what happens to the reaction when changes are imposed on the system. In which direction will the addition of iron 3 nitrate shift the equilibrium of this reaction? Observe what happens as iron 3 nitrate is added. The equilibrium shifts toward the product since the iron 3 nitrate is a source of iron 3 ions, one of the reactants in our equation. As a result, more of the iron thiocyanate ions are formed and the solution turns redder.
Okay, so this is one of the reactions, like I said before, that you'll be doing in experiment 3, hypothetically. And that's good that we had this little video because it shows what you would be seeing if you were to do this experiment hands-on. The other item that's interesting in that discussion, or that description, is that iron was added as iron 3 nitrate. Right? So what happened to the nitrate? Nobody? My cat and dog are both asleep, so they're not going to tell me what it is. Nitrate is a spectator. It does not enter the reaction. It's not part of the net reaction. Right? So what we've been looking at with the iron thiocyanate is a net reaction. So thiocyanate would be added, I think probably it's added as potassium thiocyanate. And iron could be added as this one. Let's see. We may have added it as this one. In the experiment. And it's good to use these types of chemicals because the product, iron thiocyanate, is a blood red color. In fact, if you get a high enough concentration, you may even call it brick red. It's very dark and probably exceeds its solubility, so you start getting solids. but that's a different equilibrium. You do get to do that equilibrium, right? The very first one that you do in the experiment is sodium chloride, table salt, in a saturated solution, and how do various additions to that system behave. So pay close attention to the description that I give when I go through. Be sure that you have a copy of the lab as I discuss it, because I may give you answers on the way. You can pause it, write in your answers, and save you a lot of headache. Okay.
The equilibrium between dinitrogen tetraoxide and nitrogen dioxide is dynamic. As shown, N2O4 molecules fall apart at the same rate that NO2 molecules recombine. If we change the equilibrium conditions, the equilibrium concentrations will shift according to Le Chatelier's principle. As we increase the temperature, the equilibrium shifts to the formation of additional NO2 molecules.
Ah, okay. So what type of reaction is that? If we add energy to this system in the form of heat, and it produces more product, is it exothermic or endothermic? It has to be endothermic, right? If you add heat and shift it that direction, that's the only explanation. If we shift to the products, adding heat is a reactant. So it's an endothermic reaction. Oh, we're done. Okay. Stop that share. All right. Any questions about the topic? Be sure and do your homework and take a good look at the review document, those problems, because we've only scratched the surface. The real learning comes in when you start to try to work problems in equilibrium. And that's what the review document is for, to give you practice working those problems. And then you might have some more questions. Okay, otherwise I'll see you guys on Thursday, and we'll look at that review. Okay.